Video, we're going to continue our discussion with VAR modeling. In particular, we're going to talk about VAR model forecasts, how the forecast formula works, a little bit about it. Recall that the formula for the VAR model is admittedly pretty involved, and want to look at the forecasting formula to make sure we can understand what's going on when R hands us our VAR forecast. Thankfully, that's how that's going to happen. But let's at least know where the formula comes from. The way that we'll do this is let's first of all step back and do a short review, because this is just an extension of the ARP model forecasting from Chapter 6. So that's what we will review. Recall that an AR1 model can be written as an XT. XT is an AR1 model if XT is given as phi1 times X sub t minus 1 plus 1 minus phi1 times mu plus a sub t. That's the form of an AR1 model. And as we've seen in a previous video as well, the AR1 forecast formula is, recall the notation, x hat for the forecast, t naught, that's the last value in a data set, and then the L is the steps ahead that you would like to forecast. We've seen that several times. Let's go ahead and fill this in. So x hat t naught of L would be, look up at the formula for the AR1, and we remember that phi1 gets replaced by phi1 hat. X t minus 1 gets replaced by x hat of t naught of L minus 1. So it's looking back one time point. Plus 1 minus, again, the phi1 gets replaced by phi1 hat. And mu gets replaced by x bar. And the AT goes away because the mean of AT is 0. So that's our next best guess at what that value will be. So it goes away. And that is our formula for the AR1 forecast formula. That is, if you want to look back, if you're looking at the book, 628. So back in chapter 6, formula 6.28 is the formula number. Okay, let's now extend that to the ARP. Recall that XT is called an ARP if it can be written in this form. And really, again, let's look back up at our AR1, take it out to P. So we'll have phi1 times xt minus 1, just as we did above, plus phi2 xt minus 2, and so on until you get out to phi p times x sub t minus p. So that is equivalent to this piece. Now let's talk about the phi terms and the mu terms. So instead of 1 minus phi1 mu, as it is in the AR1, we'll now need to, for the ARP, go out to 1 minus phi1 minus phi2 all the way out to minus phi p times mu plus AT. So it makes sense that that's the ARP model. And then let's go ahead and get the forecast formula for the ARP. Similar to what I did before, I wrote the formula. I referenced the formula back in chapter 6. It's formula 636. Now notice that this is in summation form. It's not written out as the way that we did it up here for 628. So let's do this. Let's ignore that line right now, and let's go ahead and fill in what we think it would be just by looking at the ARP formula, and then we'll confirm and see if that matches up with what 636 says. So just as we did before, let's look at the ARP, and let's get the forecast formula. So again, it would be x hat of t naught of L. That's the same. And then we've got phi1, so that gets replaced by phi1 hat. Xt minus 1 gets replaced by x hat of t naught of L minus 1 plus phi2 hat of x hat of t naught of L minus 2. We won't write that in just to make it look exactly like what we have up above. So the phi hat, or the phi p, will be replaced by phi hat p. The x sub t minus p will be replaced by x hat of t naught of L minus p plus, so we have this 1 minus phi1 out to minus phi p of mu. We know that the mu gets replaced by x bar. We'll put that out front. as we typically do, and then we'll have 1 minus v1 hat minus v2 hat all the way out to minus vp hat. Again, the AT has a mean of 0, so the forecast of that will be 0. And that is our forecast formula. And now let's do this. Again, as I mentioned before, let's make sure that this matches up with what Formula 636 says. It's in a different form. It's in the summation form, but it should work out for us. So it says that it should be the sum of j equals 1 to p of phi hat j times x hat of t naught of L minus j. And that's exactly what we have here, because we have phi hat 1 times x hat of t naught of L minus 1 plus, continue on, it would go to 2 and 3 and so on until it gets to p. So this piece certainly matches up with this piece. And then we have x bar times 1 minus phi 1 hat minus all the way out to phi hat p, which perfectly matches up with this. Now, you may be wondering, this video is not supposed to be about AR1s and ARPs. That's correct, but as we said before, these formulas for the VAR model are very involved. And the best way for me, anyway, to really understand the VARPs is to make sure that I take a quick little trip back to the AR1s and the ARPs, because that lets me get kind of warmed up and accustomed and reacquainted with the formulas when they look a little bit tamer, and then we're ready to jump into the big formula. That's exactly what we'll do on the next light board. So we're going to start with this, and we will then get into the details of the VARP forecasting formula. Okay, let's continue where we left off. Recall that in the last light board we were looking at the forecast formula for the AR1 model and the ARP model. I said that the reason I'd like to do that is just to take a look at the format again for those formulas. Remember how we do those, because that would make it easier to jump into this bigger bivariate VAR model. So the first thing you'll see there on the top line is the forecasting formula for the ARP model. We talked about that in detail. X hat of T naught of L equals this set of terms right here. Okay, well, the obvious question now is, well, what about the forecast for a bivariate VAR1 model? Well, just as we did on the light board before, the way that we looked at our forecast or tried to think about our forecast was, first of all, to consider what the model looked like. And we're going to do the same thing here. So let's recall the bivariate VAR1 equations. Remember, there will be two of them because there's two dependent variables. xt1 equals 1 minus phi11 times mu1 minus phi21 times mu2. Recall that that's the beta 1 piece. And then the rest of it is all about the individual phi terms, right? Times an x value depending on which variable we're talking about and depending on the number of lags. So phi11 times xt minus 1 comma 1 plus phi12 times xt minus 1 comma 2. So there's variable 1, there's variable 2, both of them looking at one lag before, plus at1. That's the residual of the variable x1, of the variable 1. What about xt2? Same type of thing. First two terms here have to do with the beta. That's the beta 2, right? And then again, we jump into the individual phi21 times xt minus 1 comma 1, phi22 xt minus 1 comma 2. What did that just do? Well, it looked at variable 1 and variable 2, looking back 2 time points ago, plus at2. And remember here, it's a good chance to talk about this real fast. So notice the convenient, very resourceful way that these VAR1 models, whenever they're predicting for variable 1, it doesn't just use information about variable 1. It brings in information, it does, there is variable 1, but it also brings in the information about variable 2 and looks at it one lag time point ago. Same thing for variable 2. For variable 2, the forecast depends on both variable 1 and variable 2. And that's the strength of the VAR models and the reason that it can provide more information than just a univariate model. So let's look at the forecast. We'll write these out just as we did on the whiteboard before for the AR1 and the ARP. It's not going to be hard. We'll just do the same type of thing we did before. So for x hat of t naught 1, strange looking notation there, but t naught, that means the last time point, variable 1 of L will be 1 minus, so I'm looking at, so this, of course, I'm looking at this equation right here. So 1 minus, we'll replace phi 1, 1 with phi 1, 1 hat. We'll replace mu 1 with x bar 1 minus phi 2, 1 will get replaced with phi 2, 1 hat. Mu 2 will get replaced by x bar 2. Phi 1, 1 will get replaced by phi 1, 1 hat. Xt minus 1 comma 1, remember we're talking about variable 1, and we're looking at 1 lag before, so that will be given by the forecast x hat of t naught 1, because we're talking about variable 1, of L minus 1. Go to the next one, the next term, phi hat 1, 2 times x hat t naught 2 of L minus 1 plus AT1. Remember the mean of that is 0, so our forecast of it is going to be 0, so it disappears. And there is your forecast formula for x hat of t naught 1 with a lag of 1. We could replace that L with 1 for that very reason. Okay, let's look at the forecast for x hat of t naught 2 with a lag of 1. And we'll look at the formula here. We'll look at this one, and it's going to be as follows. It'll be negative phi hat 2, 1 times, replace mu 1 with x bar 1 plus 1 minus phi hat 2, 2 times x bar 2 plus phi hat 2, 1, just as before, x hat, this will be 2 naught 1, or x of t naught 1, because it's variable 1, of L minus 1, plus phi hat 2, 2 times x hat of t naught 2 of L minus 1. And again, the A term goes away because the mean of that is 0. So there are your forecasts for the bivariate VAR1 model. So again, notice the efficiency, the resourcefulness of the VAR. It uses the correlation structure between the variables and among the variables, that is the independent variables, in order to make forecasts about each dependent variable. So pretty neat idea behind that, and as I said, really important to use in economic type settings. Anytime there's a leading indicator, then that gives you a good reason to consider a VAR model, because you know that there could be two variables that are related, and using that second variable can really give you some better forecasting ability and ability to model data. So in our next video, we will look at how to make these forecasts by using R. You're not going to want to do this by hand. That you can obviously see that that's going to be a big mess if you were to do that. And as I said, so in the next video, we'll look at a real example, and this example will be about sunspot and melanoma and the relationship between them. And I think you'll find that to be quite interesting. You'll see how a bivariate VAR model can be a big improvement over a univariate model. We'll see you then.